What if everything we thought we knew about gravity was incomplete? Picture this: a silent partner to the force that keeps your feet on the ground. An unseen presence tugging at the stars, bending light in ways that shouldn't be possible. This isn't science fiction. It's a tantalizing possibility hinted at by dozens of cosmic oddities that defy explanation. For centuries, we've relied on gravity as the universe's rulebook, the invisible hand guiding planets and galaxies. But what if that hand isn't working alone? Consider the Andromeda Galaxy, racing toward us faster than our equations predict, or the eerie quiet of cosmic voids, where matter seems to vanish against all logic. These aren't just quirks, they're screaming clues that something fundamental is missing from our understanding. Scientists call it modified gravity, shadow gravity, or even a gravitational doppelganger. Whatever name it goes by, the implications are staggering. We might be standing on the brink of a discovery that reshapes physics itself, rewriting textbooks and revealing a hidden layer of reality. So how do we begin to unravel this mystery? By examining the 40 most puzzling phenomena that point to gravity's secret twin. From ghostly gravitational echoes to galaxies spinning as if tugged by invisible threads, each piece of evidence pulls us deeper into the unknown. This isn't just about filling gaps in equations, it's about peering into the dark corners of the cosmos and asking, what else is out there? By the time we're done, you'll never look at the night sky the same way again. The universe is whispering its secrets. Are you ready to listen? Take a spiral galaxy like our Milky Way. Its outer stars whip around at speeds that should send them hurtling into deep space. Yet they don't. Instead, they cling to their orbits as if held by an unseen hand, moving at nearly the same speed as stars closer to the center. This shouldn't happen. According to Newton's laws, stars farther from the galactic core should slow down, like planets trailing off in our solar system. But they don't. This bizarre behavior was first spotted in the 1970s by astronomer Vera Rubin, whose observations shattered expectations. The usual explanation, dark matter, an invisible substance thought to make up most of the universe's mass, exerting extra gravitational pull. But what if the answer isn't hidden matter at all? What if gravity itself behaves differently on cosmic scales? Some theorists argue that tweaking gravity's rules, adding a shadowy twin that subtly alters its strength over vast distances, could explain these strange rotations without invoking dark matter. Picture a river flowing at the same speed no matter how wide it gets. That's the enigma of galaxy rotation. Modified gravity theories, like Mordechai Milgrom's MODIFIED Newtonian dynamics or MOND, suggest that under extremely weak forces like those at a galaxy's edge, gravity gains an unseen boost. It's as if the universe has a second rulebook for these fringe regions, one where gravity's shadow twin steps in to keep stars from flying loose. The implications are profound. If true, we wouldn't need dark matter to explain galactic behavior, just a deeper understanding of gravity's hidden mechanics. Yet the debate rages on. Some galaxies fit MOND's predictions perfectly, while others stubbornly resist. This lingering mystery keeps scientists digging, testing, and wondering. Are we missing a piece of gravity's puzzle? Or is the cosmos playing an even stranger game than we thought? Now imagine two massive galaxy clusters slamming into each other at unimaginable speeds, a cosmic wreck that should reveal gravity's deepest secrets. The Bullet Cluster collision did exactly that, but what it showed left scientists stunned. When these clusters collided, their hot gas, the visible matter, piled up in the center, slowed by friction like two clouds merging. But something far stranger happened with gravity. The way light bent around the clusters revealed that most of the gravitational pull wasn't coming from the gas at all. Instead, it seemed to follow two invisible blobs drifting away from the crash site, as if gravity itself had ghostly anchors separate from the visible universe. This bizarre separation is exactly what dark matter theories predict, an invisible substance unaffected by collisions, carrying the bulk of the mass. But here's where things get interesting. Some researchers argue this could also fit a different narrative, gravity behaving in ways we don't yet understand. What if, instead of dark matter's hidden mass, there's a second flavor of gravity at work? A shadow twin that operates independently, bending spacetime even where normal matter can't. Modified gravity theories like MOND struggle to explain the bullet cluster perfectly, but they don't rule it out entirely. Imagine gravity as a two-layered force, the familiar pull we know, plus a faint echo that lingers where matter once was, like a cosmic afterimage. It's a radical idea, but not impossible. After all, Einstein's relativity once seemed just as outlandish before it rewrote physics. The bullet cluster remains a thorn in the side of any simple explanation. Dark matter supporters see it as their strongest evidence, while gravity revisionists see tantalizing gaps. One thing's certain, this collision exposed something fundamental we're still deciphering. Whether it's invisible particles or an unseen facet of gravity itself, the universe is clearly holding back its full story. And that's what makes this mystery so thrilling. Every answer leads to deeper questions. In the vast emptiness between planets, where spacecraft glide on predictable paths calculated to perfection, something strange happened to NASA's Pioneer probes. These robotic explorers, launched in the 1970s, began drifting ever so slightly off course, as if an invisible finger were gently nudging them toward the sun. The deviation was tiny, just a fraction of what standard physics predicted, but it was undeniable. Year after year, the probes slowed more than they should have, as though space itself held a subtle resistance no one had accounted for. Scientists called it the Pioneer Anomaly, and for decades it defied explanation. At first, researchers scrambled to find conventional causes, maybe heat radiating unevenly from the spacecraft systems, or a tiny fuel leak. But after painstaking analysis, every mundane possibility was ruled out. The anomaly remained, whispering the same unsettling question: what if gravity isn't behaving the way we think it should? Some theorists began to wonder if this microscopic tug could be the fingerprint of gravity's shadow twin, an extra layer of force that only reveals itself in the quietest, most distant corners of space. Imagine dropping a feather in a vacuum chamber, expecting it to fall straight down, only to watch it veer slightly to the left every single time. That's the kind of stubborn, repeatable oddity the Pioneer probes presented. Modified gravity theories like MOND suggest that under extremely weak accelerations, like those experienced by spacecraft drifting far from the sun, gravity might gain an unexpected kick, a faint echo of its usual self. It's as if the universe has a second set of rules for these liminal zones, where familiar physics blurs into something stranger. The Pioneer Anomaly faded from headlines when newer missions, like the Cassini spacecraft, failed to detect the same effect. But the mystery never truly died. Some scientists argue that newer probes were designed differently, their trajectories more affected by internal forces, masking any subtle external tug. Others think the anomaly might still be out there, waiting to be rediscovered by a mission sensitive enough to catch it. What makes this enigma so compelling isn't just the deviation itself, but what it represents, a crack in the foundation of our understanding. If even the vacuum of space can't be trusted to play by the rules, what else might we be missing? Whether it's an unseen facet of gravity or something entirely new, The pioneer Anomaly reminds us that the cosmos loves to hide its secrets in plain sight, and sometimes the smallest clues point to the biggest revolutions. Even the most meticulously planned space missions can throw curveballs. Take the bizarre case of spacecraft suddenly gaining speed for no apparent reason. When the Galileo probe swung past Earth in 1990, scientists expected a precise gravitational boost, a routine maneuver called a gravity assist. But Galileo didn't just get a nudge, it got an extra kick, accelerating slightly faster than equations predicted. This wasn't a one-time fluke. The same thing happened with NASA, a near spacecraft in 1998, the Rosetta mission in 2005, and others. Each time, these probes picked up unaccounted speed during Earth flybys, as if some unseen force had given them a fleeting push. Dubbed the flyby anomaly, this effect is vanishingly small, just millimeters per second added to a spacecraft's velocity. But in the hyper-precise world of orbital mechanics, even microscopic deviations demand an explanation. Engineers checked every conceivable technical glitch: atmospheric drag, thruster misfires, even the pressure of sunlight. Nothing fit. The anomalies persisted, as stubborn as they were subtle. Here's where it gets intriguing. Some researchers speculate these speed boosts might hint at gravity behaving differently close to Earth, not in the way we experience it daily, but under very specific conditions. Imagine gravity as a river with hidden currents. Most of the time it flows predictably, but at certain points, like during a high-speed flyby, an undercurrent tugs just enough to alter momentum. Could this be gravity's shadow twin briefly making its presence known? Modified gravity theories struggle to fully explain the flyby anomaly, but they don't dismiss it. One hypothesis suggests Earth rotation might create a subtle, asymmetric gravitational field, a kind of space-time whirlpool that spacecraft briefly dip into, stealing a whisper of extra energy. Others wonder if these flybys expose a gap in Einstein's relativity, a scenario where extreme speeds and precise angles reveal a hidden layer of physics. What makes these anomalies so compelling isn't just the mystery, it's the timing. The effect seems to vanish when scientists look for it deliberately. Later missions, like Juno in 2013, showed no anomalous boost at all. This inconsistency only deepens the puzzle. Is the flyby anomaly a cosmic quirk that comes and goes, or are we missing a critical variable, something that only appears under perfect, fleeting conditions? Whether it's an undiscovered facet of gravity or something entirely new, these tiny speed boosts remind us that even in the clockwork precision of orbital mechanics, the universe leaves room for surprises. And sometimes the smallest deviations point to the biggest unanswered questions. Deep in the afterglow of the Big Bang, where the universe's baby photo, the cosmic microwave background, should be smooth and uniform, there's a glaring blemish. Stretching nearly 2 billion light-years across, the cold spot is a cosmic bruise, a patch of space chillingly colder than its surroundings by about 70 microkelvins. That might sound trivial, but in the finely tuned symphony of the early universe, it's like finding a frozen note in the middle of a warm melody. At first, astronomers thought it might just be a supervoid, a vast, empty region where matter thinned out, cooling the light passing through. But when they mapped it, the numbers didn't add up. The cold spot is too cold, too large, and its edges too sharp for any known void. It's as if someone carved a chunk out of spacetime itself, leaving behind a ghostly imprint. This is where gravity's shadow twin enters the picture. If an unseen gravitational force, something beyond our current equations, were warping spacetime in this region, it could theoretically stretch light waves, making them appear colder. Picture a cosmic funhouse mirror, subtly distorting the universe's oldest light in ways we're only beginning to decode. Some theories suggest this anomaly might be the fingerprint of a collision with another universe, a bubble from the multiverse brushing against ours. Others propose it's evidence of gravity behaving differently at scales so vast, our models can't yet grasp it. What makes the cold spot so compelling isn't just its existence, it's the defiance. Standard cosmology struggles to explain it without invoking exotic physics. Dark energy, dark matter, even quantum fluctuations during inflation fall short. This isn't just a missing puzzle piece, it's a piece from a different puzzle altogether, one that might force us to rewrite the rules of gravity on cosmic scales. And here's the kicker, the cold spot isn't alone. Smaller cold anomalies pepper the cosmic microwave background, each a potential clue. If these are echoes of gravity's hidden twin, they could be the universe's way of whispering secrets we're only now learning to hear. Whether it's a flaw in our models or a doorway to new physics, one thing's clear. The cold spot is a cosmic riddle begging to be solved, and the answer might change everything. Our cosmic neighborhood isn't just quiet, it's eerily empty. The Milky Way floats inside a staggering expanse known as the KBC void, a bubble of near-nothingness stretching over 2 billion light-years across. To put that in perspective, if the universe were a bustling city, we'd be tucked away in a deserted alleyway, far from the bright lights and crowded streets of galaxy clusters. Most voids are expected to be modest in size, but this one defies expectations, dwarfing even the largest known structures. And here's the twist, the scarcity of matter here doesn't quite line up with how gravity should behave. Normally, voids expand gently as the universe grows, their emptiness stretching like taffy. But the KBC void's sheer scale suggests something else might be at work, a gravitational imbalance, as if an unseen hand is propping open the cosmic door, keeping this region emptier than it ought to be. One explanation, a shadowy gravitational influence, something that counters the pull of visible matter, preventing galaxies from clustering here as they do elsewhere. Imagine blowing up a balloon with a weak spot that never stretches quite like the rest. That's the KBC void, a cosmic anomaly where the rules seem subtly different. Some theorists propose this void could be a fingerprint of modified gravity at work. If gravity's strength varies depending on the density of matter around it weaker in sparse regions like voids, it might explain why this expanse stayed so barren. Others wonder if dark energy, the mysterious force accelerating the universe's expansion, acts more aggressively here, pushing matter away like an invisible tide. But the most tantalizing idea, that this void is a relic of gravity's shadow twin, a secondary force that subtly reshapes the cosmos in ways we're only beginning to detect. What makes this void so compelling isn't just its size, it's the way it challenges our cosmic maps. If voids like this are more common than we thought, it could mean the universe's structure isn't just shaped by gravity as we know it, but by hidden layers of influence waiting to be uncovered. The KBC void isn't just an absence, it's a question written in the negative space of the cosmos, and the answer might rewrite the story of how everything fits together. The cosmic microwave background is often called the universe's baby picture, a near-perfect snapshot of the early cosmos glowing with ancient light. But when scientists mapped its faint whispers, they stumbled on something unsettling. Instead of the expected randomness, a strange pattern emerged. Hot and cold spots aligned along a mysterious corridor, as if the universe had quietly drawn a line in the sand. Researchers dubbed it the axis of evil not for any malevolence, but because it defies one of cosmology's most sacred principles, that the universe on large scales should look the same in every direction. This cosmic axis isn't just a minor quirk, it's a direct challenge to the idea of isotropy, the assumption that the universe has no preferred direction, no cosmic north or south. Yet here we are, staring at a ghostly line that stretches across the sky, linking anomalies that shouldn't be connected. Imagine rolling a dice 1,000 times and always getting a 3. That's the level of statistical weirdness we're dealing with. The odds of this alignment happening by chance are astronomically low, leaving scientists scrambling for explanations. One possibility: gravity's shadow twin. If an unseen gravitational force, something beyond Einstein's equations, were subtly warping spacetime on the largest scales, it could create a hidden framework, a cosmic skeleton that nudges matter and energy into unexpected alignments. Picture a vast, invisible magnet gently pulling the universe's fabric into a faint but detectable order. Modified gravity theories suggest that under certain conditions, gravity might not be perfectly uniform. Instead, it could have a whisper of directionality, a preference imprinted in the cosmos's earliest moments. Then there's the multiverse angle. Some theorists propose that the axis of evil could be a bruise, a remnant of our universe brushing against another in the multiverse, leaving behind a gravitational fingerprint. It's a wild idea, but not impossible. After all, if other universes exist beyond our own, their gravity might seep through, tweaking the structure of spacetime in ways we're only beginning to detect. But here's the real puzzle. The axis of evil isn't just a one-off. Other large-scale anomalies, like the alignment of galaxy spins and the motion of galaxy clusters, seem to echo this mysterious directionality. It's as if the cosmos is trying to tell us something, that our understanding of gravity and even the universe's fundamental symmetry might be missing a crucial piece. Whether it's a flaw in our models or a glimpse of deeper physics, the axis of evil refuses to be ignored. It's a cosmic riddle written in the oldest light we can see, and cracking it could rewrite everything we thought we knew about the universe's structure and the hidden forces that shape it. The Hubble constant, the number that tells us how fast the universe is expanding, should be the same no matter how you measure it, but here's the catch: it isn't. When scientists calculate it using the cosmic microwave background, the afterglow of the Big Bang, they get one value. Yet when they measure it by observing pulsating stars and exploding supernova in the nearby universe, they get another. The gap between these numbers isn't just a rounding error. It's a full-blown crisis in cosmology known as the Hubble tension, and it's only getting worse as our tools grow sharper. Think of it like trying to clock the speed of a car with two different radar guns. One says 60 miles per hour, the other says 73. You'd assume one of them is broken. But in this case, both methods are backed by mountains of evidence, meticulous cross-checks, and decades of refinement. The discrepancy isn't going away. It's solidifying into a glaring contradiction that suggests something fundamental is missing from our understanding of cosmic expansion. This is where gravity's shadow twin could step in. If an unseen gravitational force were subtly tweaking how space stretches, it might explain why distant and nearby measurements don't match. Picture a rubber band being pulled from both ends, except one hand is stronger than the other, creating uneven tension. Modified gravity theories propose that on the largest scales, this secondary force might alter how galaxies move, bending the fabric of spacetime in ways that masquerade as an accelerated expansion. But the plot thickens. Some researchers argue the tension might not be about gravity at all. It could signal exotic dark energy growing stronger over time, or even particles we've yet to discover interacting with the cosmos in unexpected ways. Others wonder if the universe isn't as uniform as we thought, with pockets of space expanding faster than others like bubbles in a boiling pot. What makes the Hubble tension so electrifying isn't just the mystery, it's the stakes. If this discrepancy points to new physics, it could mean rewriting the textbooks on everything from the Big Bang to the fate of the cosmos. Every new observation deepens the puzzle, and until we crack it, the universe is holding its cards close. One thing's certain, the Hubble tension isn't just a problem to solve, it's a doorway, and what's on the other side might change everything. Galaxy clusters aren't just drifting, they're racing. In 2008, astronomers studying hundreds of these colossal structures noticed something chilling. They were all moving in the same direction at breakneck speeds, as if swept up in a cosmic current. This wasn't just random motion, it was a coordinated march toward a point beyond the edge of our observable universe. Scientists called it the dark flow, and it defies everything we know about cosmic expansion. The universe should be stretching evenly in all directions, like rising bread dough. Yet here we are, watching entire clusters of galaxies stream toward an invisible horizon, pulled by something we can't see or explain. The numbers are staggering. These clusters are hurtling at nearly 2 million miles per hour, far faster than the universe's expansion should allow, even more baffling. The flow extends billions of light years, far beyond the reach of any known gravitational force. It's as if the universe has a hidden magnet, and we're just beginning to sense its pull. The most unsettling part, whatever's causing this motion lies outside our cosmic horizon, in regions of space too distant for their light to ever reach us. One explanation points to gravity's shadow twin, a secondary force stretching beyond the visible universe, tugging at matter from realms we can't observe. Picture a vast ocean with currents flowing deep beneath the surface. We're only seeing the ripples on top, unaware of the forces moving beneath. Modified gravity theories suggest this could be a cosmic undercurrent, a gravitational echo from something colossal lurking in the unseeable dark. Then there's the multiverse angle. If our universe is just one bubble in a froth of others, the dark flow might be the gravitational wake of a neighboring universe brushing against ours. Imagine two ships passing in the night, their hulls never touching but their wakes intertwining. The idea is speculative but not impossible. After all, if other universes exist, their gravity could seep through the boundaries, nudging our galaxy clusters like leaves caught in a crosswind. But here's the twist. The dark flow isn't just a curiosity, it's a direct challenge to cosmology's bedrock principles. If gravity or some unseen force can reach across unfathomable distances, it means our understanding of the universe's structure is missing a critical piece. Whether it's a flaw in Einstein's equations or evidence of something entirely new, the dark flow forces us to confront an uncomfortable truth. The cosmos might be far stranger and far more connected than we ever imagined. What makes this mystery so gripping isn't just the scale, it's the implication. If galaxy clusters are being pulled by something beyond our cosmic horizon, it means there's more to the universe than what we can observe. The dark flow isn't just a puzzle, it's a glimpse into the unknown, a whisper from the edges of reality itself. And that's what makes science so thrilling sometimes. The biggest discoveries begin with a simple question: what's pulling us? Somewhere beyond the Milky Way's dusty veil, an invisible force is reeling us in. Our galaxy, along with hundreds of others, is hurtling toward a gravitational epicenter so powerful it warps the very fabric of space-time around it. Astronomers call it the Great Attractor, a cosmic mystery lurking 30,000 times farther than the distance to Andromeda, yet its true nature remains hidden behind a curtain of stars and interstellar dust. Here's what makes it so baffling. When scientists first mapped this motion in the 1970s, they expected to find a colossal cluster of galaxies, something massive enough to explain the relentless pull. But when they peered through the murk of our own galaxy's disk, the numbers didn't add up. The Great Attractor's gravitational grip is far stronger than any visible structure should account for. It's as if we're being drawn toward a ghost, a cosmic heavyweight cloaked in shadows. Some theories point to an immense concentration of dark matter, an unseen scaffold tugging at the universe's visible structures. But others wonder if this could be something stranger, a place where gravity's shadow twin flexes its influence. Picture a whirlpool in space, not just from the mass we can see, but from an additional, invisible current swirling beneath the surface. Modified gravity theories suggest that under certain conditions, gravity might amplify in unexpected ways, creating hotspots where its effects ripple far beyond what matter alone can explain. Then there's the location. The Great Attractor sits in what's called the Zone of Avoidance, a region of the sky obscured by the Milky Way's dense gas and dust. It's like trying to spot a lighthouse through a thunderstorm. Even with infrared and radio telescopes piercing the gloom, the core of this anomaly stays frustratingly elusive. Could it be hiding more than just a cluster? Some speculate it might be a gravitational nexus, a crossroads where multiple cosmic flows converge, magnifying its pull beyond normal limits. What makes this enigma so thrilling isn't just the mystery of what's pulling us, it's the scale. The Great Attractor isn't acting alone. Beyond it lies an even vaster structure, the Shapley supercluster, a sprawling metropolis of galaxies that might be the true end point of this cosmic river. But here's the twist, even Shapley's immense gravity can't fully account for our motion. Something else is out there, amplifying the pull, and the Great Attractor might be the middleman in a chain of gravitational secrets we're only beginning to untangle. Whether it's a hidden supercluster, a flaw in our understanding of gravity, or evidence of something entirely new, one thing's clear: the Great Attractor is more than a destination. It's a clue, a cosmic signpost pointing toward forces we've yet to name. And until we peer deeper into the darkness behind our galaxy's veil, the universe will keep its most tantalizing secrets just out of reach. Galaxies are supposed to be social creatures, thriving in crowded clusters where gravity weaves them into vast cosmic webs. But scattered across the universe's emptiest stretches, there are rebels, lonely galaxies floating in near-total isolation, where the rules of structure formation seem to break down. These are the void galaxies, and their very existence is a gravitational paradox. According to our models, these islands of stars shouldn't form at all, let alone survive for billions of years in the sparse deserts between cosmic filaments. Yet they persist, glowing defiantly in the darkness like lighthouses with no shore to guide. The problem starts with their birthplace. Galaxies typically grow where matter pools, dense knots in the cosmic web where gas and dark matter clump together, seeding star formation. But void regions are the opposite, vast, almost empty bubbles where matter is so thinly spread, gravity struggles to pull anything together. Imagine trying to build a sandcastle with grains scattered miles apart. That's the challenge void galaxies face. Yet somehow, against all odds, they've assembled themselves in places where gravity's grip should be too weak to do the job. One clue lies in their strangeness. Void galaxies tend to be smaller, bluer, and more irregular than their cluster-dwelling cousins, as if they've been frozen in an early stage of development. Without the gravitational tug of war typical in crowded galactic neighborhoods, their gas doesn't get stripped away, leaving them oddly pristine. But here's the puzzle. Even with these quirks, simulations struggle to explain how enough material could accumulate in such barren regions to form galaxies in the first place. This is where gravity's shadow twin might step in. If an unseen force subtly alters how gravity behaves in low-density environments, giving it an extra nudge where matter is scarce, it could explain how these isolated galaxies coalesce. Picture a safety net woven into the fabric of space itself, catching sparse gas and dust just enough to let stars spark. Modified gravity theories like MOND suggest gravity might strengthen in these extreme voids, counteracting the expected weakness and providing the extra pull needed to birth galaxies where none should exist. Yet the mystery deepens when we look at their survival. Void galaxies aren't just forming, they're enduring, often for billions of years, without the protective halo of a cluster. Normally, such isolation would leave them vulnerable, their gas reservoirs evaporating into the void. But many show signs of ongoing star formation, as if they've found a way to thrive in the cosmic equivalent of a food desert. Could there be a hidden mechanism, a secondary gravitational influence acting like an invisible scaffold, stabilizing these fragile structures? The implications are profound. If void galaxies owe their existence to an unseen facet of gravity, it would mean our understanding of structure formation is missing a critical variable. These lonely galaxies aren't just cosmic oddities, they're stress tests for our theories, revealing where the math falls short. Every one we discover is a whisper from the universe, hinting that gravity's story might have chapters we've yet to read. And that's what makes them so fascinating. They're not just defying expectations, they're inviting us to rewrite them. We think we've got a pretty good inventory of the universe's contents: stars, planets, gas, dust. But here's the cosmic accounting error no one saw coming. Half the universe's normal matter is simply missing. Not dark matter, not exotic particles, ordinary protons, neutrons, and electrons, the stuff that makes up everything we can see, from galaxies to coffee cups. Scientists call this the missing Baryon problem, and it's not just a small oversight. Based on the universe's gravitational blueprint, there should be twice as much normal matter as we've actually detected. So where did it all go? The first clue comes from the cosmic microwave background, the afterglow of the Big Bang. By measuring its subtle ripples, scientists can calculate how much ordinary matter baryons the universe started with. But when they tally up all the visible matter today, stars, gas clouds, galaxies, the numbers fall shockingly short. It's like checking your bank statement and realizing half your savings have vanished without a trace. The discrepancy isn't trivial. We're talking about enough missing mass to build trillions of galaxies, all somehow hiding in plain sight. One leading theory suggests these lost baryons might be lurking in vast, diffuse filaments of hot gas strewn between galaxies, cosmic spiderwebs too faint to see with traditional telescopes. Picture steam rising from a boiling pot, invisible until the light hits it just right. In recent years, advanced instruments have begun detecting whispers of this warm, hot intergalactic medium, or WHIM, but even these discoveries only account for a fraction of the deficit. The rest remains stubbornly elusive. This is where gravity's shadow twin enters the conversation. If an unseen gravitational influence were subtly altering how normal matter clumps or disperses, it could explain why so much of it has slipped through our observational nets. Imagine a force that doesn't just pull matter together, but also tweaks its behavior, keeping gas clouds so thinly spread they evade detection, or locking baryons into exotic, low-energy states we can't yet measure. Modified gravity theories propose that under certain conditions, gravity might have a secondary effect, one that nudges ordinary matter into hiding without breaking the known laws of physics. But there's another, wilder possibility. What if the missing baryons aren't missing at all, but transformed? Some researchers speculate they could be bound up in strange, ultralight particles, or even woven into the fabric of spacetime itself, contributing to gravity in ways we don't yet understand. It's like realizing your missing keys were in your pocket the whole time, just in a form you didn't recognize. The stakes here are higher than they seem. Solving the missing baryon problem isn't just about balancing the universe's books. It's about testing the limits of our cosmic models. If gravity's shadow twin is masking half the normal matter in existence, it means we're not just missing matter. We're missing an entire layer of reality's rules, and until we find those lost baryons, the universe will keep its biggest accounting secret locked away. The early universe should have been a cosmic nursery, a place where galaxies took their time growing up, slowly gathering gas and dust over billions of years. But when astronomers peered back to just a few 100 million years after the Big Bang, they found something shocking. Galaxies already fully grown, colossal structures gleaming with stars far sooner than any model predicted. These are the too big to exist galaxies, cosmic Goliaths that shouldn't have had time to form, yet there they are, shining defiantly in the darkness of the infant universe. Take the mammoth galaxy SPT-03116, for example. Spotted by the South Pole Telescope, this behemoth existed when the universe was barely 800 million years old, a toddler by cosmic standards. Yet it's as massive as our Milky Way, which took over 13 billion years to reach its current size. How could something so enormous assemble itself so quickly? Current theories suggest galaxies grow through gradual mergers, like snowballs rolling downhill, gathering mass slowly. But these ancient giants seem to have skipped the intermediate steps, appearing almost fully formed out of nowhere. The implications are staggering. If galaxies can bulk up this fast, it means our understanding of cosmic evolution is missing a critical ingredient, one tantalizing possibility. A shadow gravitational force, something that turbocharged star formation in the early universe, pulling matter together at breakneck speeds. Picture gravity with an unseen accomplice, a partner that amplifies its pull in dense environments, allowing galaxies to feast on gas and dust far more efficiently than we thought possible. Modified gravity theories hint that under extreme conditions, like those in the primordial universe, gravity's rules might shift, creating pockets where matter collapses into galaxies almost overnight. But here's where it gets even stranger. These early giants aren't just big, they're mature. Their stars show signs of advanced age, meaning they must have formed even earlier than the galaxies themselves. It's like finding a fully grown oak tree in a forest that sprouted just weeks ago. Some researchers speculate this could point to a two-stage process, an initial burst of hyper-fast star formation, perhaps triggered by exotic physics in the early universe, followed by rapid galactic assembly. Others wonder if dark matter, the invisible scaffolding thought to guide galaxy growth, behaved differently back then, clumping together more aggressively to seed these cosmic titans. Yet the most radical idea is that we're seeing gravity's shadow twin in action. If an additional force were at work in the dense, high-energy environment of the young cosmos, it could explain how these galaxies built themselves so quickly. Imagine a cosmic cheat code, a hidden mechanism that allowed matter to bypass the usual bottlenecks and condense into galaxies at impossible speeds. This wouldn't just rewrite the story of galaxy formation. It would mean the early universe operated under a different set of rules, ones we're only beginning to glimpse. What makes these too big to exist galaxies so electrifying isn't just their size, it's the questions they raise. Are they cosmic outliers, rare flukes in an otherwise predictable process? Or are they proof that our models of the early universe need a fundamental overhaul? Every new discovery pushes the boundaries of what we thought was possible, reminding us that the cosmos loves to defy expectations. And if these galaxies are any indication, gravity's secrets might be hiding in plain sight, written in the stars of the universe's first giants. Black holes aren't just cosmic vacuum cleaners, they're shredders. According to Einstein's general relativity, when something crosses a black hole's event horizon, it's gone for good, crushed into oblivion by unimaginable gravity. But here's the catch. Quantum mechanics insists that information, the fundamental details of what that object was, can never truly be destroyed. This clash between the universe's two most successful theories is the black hole information paradox, and it's one of the most urgent mysteries in physics. If black holes really erase information, they're breaking the rules of reality itself. Unless, of course, gravity has a shadow twin working behind the scenes to preserve what seems lost. Picture a library where every book fed into a furnace leaves no ash, no smoke, just empty space where knowledge once existed. That's the nightmare scenario physicists face when they apply quantum theory to black holes. In the 1970s, Stephen Hawking showed that black holes aren't entirely black. They slowly leak radiation and eventually evaporate. But here's the twist: that radiation appears random, carrying no trace of the information swallowed by the hole. It's like burning a library and claiming the heat radiating from the flames holds no memory of the books. Quantum mechanics says that's impossible. Information might get scrambled, but it can't vanish. So where does it go? This is where gravity's shadow twin could rewrite the story. Some theorists propose that black holes don't destroy information. They encode it in ways we can't yet detect. Imagine a cosmic backup drive. As matter falls into a black hole, an unseen gravitational influence might imprint its data onto the fabric of spacetime itself, preserving it in a hidden dimension or a quantum fog at the hole's boundary. Modified gravity theories suggest that if gravity operates differently at the extremes of a black hole's grip, it could create a failsafe, a way to stash information even as the visible universe loses track of it. Then there's the holographic principle, the mind-bending idea that all the information inside a black hole might be stored on its two-dimensional surface, like a cosmic QR code. If gravity's shadow twin is real, it could be the architect of this encoding, translating three-dimensional matter into a flat, holographic record. Think of it as the universe's way of compressing a hard drive before it's tossed into the void. The data isn't gone, it's just locked in a language we're still learning to read. But the paradox deepens when we consider what happens when black holes evaporate. If the radiation they emit truly carries no information, then the original data is lost forever. Yet experiments with quantum entanglement suggest that information is fundamentally indestructible. It can be hidden but never erased. This contradiction has led some physicists to propose radical solutions, like firewalls, violent walls of energy at the event horizon that destroy incoming matter but somehow preserve its quantum details. Others suggest black holes might spawn baby universes, shipping the information off to another reality entirely. What makes this paradox so electrifying isn't just the mystery, it's the stakes. Solving it could reveal a hidden layer of physics, a bridge between gravity and quantum mechanics that's eluded us for a century. If gravity's shadow twin is quietly preserving information, it would mean black holes aren't the end of the story, they're the beginning of a new chapter. Every photon they emit, every ripple in spacetime they create, might hold a clue to the universe's most guarded secret, how it remembers itself. And that's what keeps physicists staring into the abyss, not just to see what's lost, but to discover what's waiting to be found. Rising from the heart of the Milky Way like twin titans, the Fermi bubbles stretch 50,000 light-years into space, one erupting above the galactic plane, the other plunging below. These colossal structures, glowing with high-energy gamma rays, were only discovered in 2010 by NASA Fermi telescope, hidden in plain sight against the backdrop of the cosmos. What's shocking isn't just their size, it's the sheer energy they contain, equivalent to 100,000 exploding stars. Yet no supernova, no known black hole activity, no standard astrophysical process can fully explain their origin. They're cosmic graffiti sprayed across the galaxy by a force we've yet to decipher. The leading theory points to our galaxy's supermassive black hole, Sagittarius, a star, which might have erupted in a cataclysmic outburst millions of years ago, spewing jets of particles that inflated these bubbles. But here's the catch: the energy signatures don't quite match. The gamma rays are too evenly distributed, too symmetrical, as if shaped by something more deliberate than a black hole's messy tantrum. That's where gravity's shadow twin enters the scene. If an unseen gravitational force were interacting with dark matter near the galactic center, it could trigger annihilation reactions on a staggering scale, like invisible matchsticks striking against the fabric of spacetime, igniting these persistent beacons. Imagine a candle flickering in a sealed room. Now replace the candle with a nuclear blast and the room with the galaxy. That's the level of containment we're dealing with: energy bursting outward yet sculpted into near-perfect lobes. Modified gravity theories suggest that if dark matter interacts with a secondary gravitational field, it could release energy in controlled, symmetrical waves, creating structures just like the Fermi bubbles. It's as if the galaxy has a hidden pressure valve, one tuned to frequencies we're only beginning to sense, but the plot thickens when we look at their timing. The bubbles are relatively young in cosmic terms, perhaps a few million years old. That raises an eerie question: was this a one-time event, or are we witnessing a recurring cycle? Some researchers speculate these could be gravitational aftershocks, ripples from a recent collision with a dark matter subhalo, or even evidence of a dormant force that periodically awakens near the galactic core. What makes the Fermi bubbles so mesmerizing isn't just their grandeur, it's the way they defy categorization. They're not quite black hole echoes, not quite dark matter fireworks, but something in between. Like smoke rings from a cosmic cannon, they linger in the sky, hinting at forces operating just beyond the edge of our understanding. And until we crack their code, they'll remain one of the Milky Way's most dazzling enigmas, a reminder that even in our home galaxy, the universe still has secrets to spill. Galaxies aren't just islands of stars, they're cosmic engines, breathing in gas and sometimes exhaling it at velocities that defy logic. These aren't gentle breezes but supersonic tempests, blasting material outward at millions of miles per hour, fast enough to strip entire galaxies of their star-forming fuel. What's propelling these violent galactic winds? The usual suspects: supernova explosions. Black hole jets fall short of explaining their sheer power and scale. Some of these outflows are so extreme, they fling gas clear out of their host galaxies, leaving behind voids where new stars should be blooming. It's as if an invisible hand is flicking matter into the cosmic void, and gravity, as we know it, isn't strong enough to hold on. Take the nearby starburst galaxy M82, a textbook case of this phenomenon. Here, gas races outward at speeds approaching 2,000 kilometers per second, enough to cross the continental United States in less than a second. Traditional models attribute this to the collective force of exploding stars, but the math doesn't quite add up. The energy required exceeds what stellar explosions alone should produce, like trying to launch a rocket with firecrackers. Something else is amplifying these winds, and one tantalizing possibility is a hidden gravitational influence. Imagine a galaxy not just anchored by its visible mass but also tethered to an unseen force, one that tugs at gas clouds just enough to destabilize them, sending them careening outward. Modified gravity theories suggest that in regions of intense star formation where matter is densely packed, gravity's shadow twin might kick in, adding an extra push to these outflows. Picture a child on a swing. Normal gravity pulls them downward, but if another force subtly nudged them at just the right moment, they'd soar higher than expected. That's the kind of subtle interference some researchers think could be at work in these galactic gales. But the plot thickens when we look at quasar-driven winds, where supermassive black holes are the presumed culprits. Even here, the numbers are perplexing. Some quasars eject gas with such force that it should rip their host galaxies apart, yet these structures remain intact. It's like a hurricane blowing through a house of cards without toppling it, an impossible balance unless gravity is playing by different rules in these extreme environments. Could there be a secondary force counteracting the chaos, stabilizing galaxies even as their guts are being blown outward? The implications ripple far beyond these individual galaxies. If galactic winds are stronger and more frequent than our models predict, it could explain why the universe's star formation has slowed over time. These outflows might be cosmic regulators, shutting down galaxy growth by expelling the raw materials needed to make new stars. And if gravity's shadow twin is indeed part of the equation, it would mean our understanding of galactic evolution is missing a fundamental piece, one that silently shapes the fate of galaxies from behind the curtain. What makes this mystery so compelling isn't just the violence of these winds, but their precision. They don't spew gas randomly. They often form intricate structures, filaments, bubbles, even vast cones of ejected material. It's as if the universe is sculpting with these outflows, carving patterns that hint at an underlying order we've yet to decode. Whether it's an unseen facet of gravity or something entirely new, one thing is clear: the forces shaping galaxies are far more nuanced and far more mysterious than we ever imagined. The Milky Way should be surrounded by a bustling entourage of small satellite galaxies, cosmic minions orbiting their giant parent like moths around a flame. According to supercomputer simulations of galaxy formation, our cosmic neighborhood ought to host hundreds of these dwarf galaxies, leftovers from the universe's chaotic early days. Yet when astronomers count them, the numbers fall shockingly short. We've found barely 60, a cosmic census so incomplete it suggests something or someone has been quietly erasing galaxies from the ledger. This discrepancy isn't just a minor accounting error. The missing satellites problem strikes at the heart of our understanding of how structure forms in the universe. If dark matter behaves as we think it should, these tiny galaxies would be the natural byproduct of smaller clumps of dark matter merging with larger ones, seeding star formation along the way. Their absence implies a fundamental flaw in our cosmic recipe. Either dark matter isn't clustering the way we predict, or some unseen force is suppressing galaxy formation altogether. Enter gravity's shadow twin. What if an additional gravitational influence subtly alters how matter behaves in these satellite systems? Picture a cosmic filter, one that allows only the densest, most resilient gas clouds to collapse into stars, while the rest remain scattered and dark. Modified gravity theories like MOND suggest that in low-density environments, such as the outskirts of galaxies, gravity might weaken just enough to prevent fragile gas clouds from ever coalescing into visible structures. It's like trying to light a campfire in a stiff breeze. Only the sturdiest kindling will catch flame while the rest blows away. The plot thickens when we examine the satellites we have found. Many are oddly diffuse, ghostly galaxies like Antlia 2, so faint they barely register against the night sky. Others, like the ultra-faint dwarfs near the Milky Way's plane, seem to be missing almost all their dark matter, as if something stripped it away. Could gravity's shadow twin be selectively pruning these systems, leaving behind only the most tenuous survivors? Then there's the distribution problem. The satellites we observe aren't just scarce, they're arranged in a bizarrely flat plane around the Milky Way, orbiting like cars on a cosmic roundabout. This shouldn't happen randomly. If dark matter is as chaotic as simulations suggest, these galaxies should be scattered in all directions like bees around a hive. Their orderly alignment hints at an unseen structure, perhaps a gravitational framework sculpting their orbits from behind the scenes. One radical explanation. These satellites aren't missing at all, they're just invisible. Some theorists propose that thousands of dark galaxies could be lurking undetected, their stars so sparse they're lost in the Milky Way's glare. Others wonder if tidal forces, the gravitational tug of war between galaxies, have shredded most of the dwarfs into streams of stars, leaving only the hardiest intact. But even these theories struggle to close the gap entirely. What makes this mystery so tantalizing isn't just the missing galaxies, it's what their absence implies about the universe's hidden scaffolding. If gravity's shadow twin is quietly shaping the cosmic landscape, it would mean our simulations aren't wrong, they're just incomplete. Every undetected dwarf, every strangely aligned orbit, is a breadcrumb leading us toward a deeper truth. The universe might be playing by a second set of rules, written in the language of forces we've yet to name. And until we crack that code, the Milky Way's missing satellites will remain one of cosmology's most stubborn puzzles, a galactic whodunit with no culprit in sight. Quasars should be cosmic lighthouses, their light shifting predictably as the universe expands, their redshifts acting like mile markers on the highway of space. But some of these brilliant beacons defy the rules, displaying redshifts so bizarre they seem to thumb their noses at cosmology itself. Take the case of quasar pairs physically linked by filaments of gas, yet separated by redshift values so different they shouldn't belong to the same era of the universe. It's like finding two candles tied by the same wick, one burning twice as fast as the other for no apparent reason. These anomalies aren't just academic curiosities, they're potential cracks in the foundation of how we measure cosmic distances. Redshift, the stretching of light toward longer wavelengths as space expands, is supposed to be our most reliable gauge of how far away objects are. But when quasars, some of the brightest, most energetic objects in existence, show redshifts that don't match their surroundings, it forces us to ask, is something else tugging at the fabric of spacetime, warping light in ways we haven't accounted for? One possibility is that gravity's shadow twin leaves fingerprints on light itself. Imagine spacetime not as a smooth rubber sheet, but as a layered fabric, with an unseen gravitational force subtly bending light as it passes through. Modified gravity theories suggest that in extreme environments like the violent neighborhoods around quasars, this secondary influence might amplify or distort redshifts, creating mismatches that baffle astronomers. Picture a prism not just refracting light but editing it, altering its wavelengths before they reach our telescopes. Then there's the peculiar clustering of these anomalies. Some quasars with discordant redshifts appear to line up in strange, geometric patterns across the sky, as if arranged by an invisible hand. Could these alignments point to large-scale structures warping spacetime in ways we can't yet map? Or might they hint at something more radical, that light interacts with hidden dimensions or unknown fields as it traverses the cosmos? The implications ripple far beyond quasars. If redshifts aren't the steadfast rulers we thought, it could mean our cosmic distance ladder, the tool we use to measure the universe's expansion, has a hidden wobble. That would throw everything from the age of the universe to the nature of dark energy into question. It's like discovering your tape measure has been stretching unpredictably all along, casting doubt on every blueprint you've ever drawn. Yet the most tantalizing clue lies in the outliers themselves. These anomalous quasars often exhibit other oddities, unusual brightness fluctuations, jets of matter moving at impossible speed. It's as if they're not just cosmic anomalies but messengers, broadcasting signals from a frontier where gravity's rules bend. Whether it's an unseen force tweaking spacetime or a flaw in our models, one thing's clear: the universe's brightest beacons might be shining a light on its deepest secrets. And until we decode their contradictions, the redshift controversy will keep pulling us toward the edge of the unknown. The universe is supposed to be a masterpiece of symmetry, a vast, evenly distributed tapestry where matter spreads uniformly in all directions. But when astronomers map its largest structures, they find something startling. The cosmos has a distinct tilt, a lopsidedness that defies expectations. Galaxies cluster more densely in one hemisphere than the other. Superclusters stretch into bizarrely elongated shapes, and even the cosmic microwave background shows subtle asymmetries, like a painting with heavier brushstrokes on one side. This isn't just random variation, it's a systematic skew, as if the universe itself has a dominant hand. Take the so-called dipole repeller, a vast region of space so empty it seems to be pushing galaxies away. On the opposite side of the sky, the Shapley supercluster exerts an equally disproportionate pull, creating a cosmic tug-of-war with our Milky Way caught in the middle. This imbalance isn't trivial. The forces at play suggest something beyond the gravity of visible matter, something tipping the scales on a universal level. Could this be the work of gravity's shadow twin, a secondary force subtly warping the distribution of matter over cosmic time? Here's where it gets even stranger. Simulations of the universe's evolution, based on standard physics, struggle to reproduce these large-scale asymmetries. They predict a more balanced cosmos, one where matter disperses evenly like ink in water. Yet the real universe looks more like a spilled glass, pooling unevenly across the table. One explanation: an unseen gravitational influence that doesn't just pull matter together, but nudges it in preferred directions. Picture a game of billiards where an invisible player occasionally leans on the table, altering the paths of the balls just enough to skew the outcome. Modified gravity theories offer a tantalizing possibility. What if gravity's strength varies not just with distance but with orientation? Imagine a universe where spacetime has a faint grain, like wood, making it easier for structures to form along certain axes. This could explain why superclusters filament along specific alignments, or why voids like the KBC void grow disproportionately large. It's as if the cosmos has hidden currents, and gravity's shadow twin is the unseen tide guiding matter into its uneven arrangement. The implications are profound. If the universe's lopsidedness stems from an undiscovered facet of gravity, it would mean our models of cosmic evolution are missing a critical variable, one that's been quietly shaping the universe's architecture since the beginning. From the distribution of galaxies to the alignment of black hole spins, these asymmetries might be cosmic breadcrumbs leading us toward a deeper truth, that gravity, as we know it, is only half the story. And until we decipher the forces behind this grand imbalance, the universe will remain a puzzle, one where the pieces fit, but never quite symmetrically. Fast radio bursts are among the most explosive mysteries in the cosmos. Blasts of radio waves, so powerful they outshine entire galaxies for milliseconds before vanishing without a trace. But a handful of these cosmic firecrackers refuse to play by the rules. Instead of fading into oblivion, they burst back to life weeks, months, or even years later, pulsing with the erratic rhythm of a malfunctioning beacon. These are the repeater FRBs, and their stubborn reappearances have physicists scratching their heads. Take FRB 121102, the first known repeater, discovered in 2016. Unlike its one and done cousins, this celestial strobe light has erupted hundreds of times from the same patch of sky near a dwarf galaxy 3 billion light-years away. Its bursts aren't just repetitive, they're chaotic, arriving in unpredictable clusters with no discernible pattern. It's as if something is flicking a cosmic switch at random intervals. channeling unimaginable energy into these fleeting flashes. The leading theories colliding neutron stars, magnetar flares, or black hole hiccups struggle to explain the sheer irregularity. Neutron star mergers are catastrophic, one-time events, while magnetars typically flare with some semblance of periodicity. These repeaters defy both templates, sparking wilder ideas. Could gravity's shadow twin be the unseen conductor? Picture a neutron star, already a dense, magnetized monster, interacting with an invisible gravitational field. As this secondary force tugs on the star's crust, it might trigger sporadic energy releases, like a bell struck by an unseen hammer. Modified gravity theories suggest that in extreme magnetic environments, like those around magnetars, an additional gravitational influence could warp spacetime just enough to destabilize the star's surface periodically. Imagine a trampoline with an extra spring no one knew about. Sometimes it buckles under pressure, sometimes it holds firm. This wouldn't just explain the randomness, it could account for the burst's staggering energy. If gravity's shadow twin amplifies magnetic reconnection events, sudden rearrangements of magnetic field lines, it might unlock reservoirs of energy beyond what standard physics predicts. Then there's the localization problem. Some repeaters, like FRB 180916, appear to originate near massive galactic structures but not precisely within them. This odd positioning hints at something stranger. Perhaps these bursts aren't coming from neutron stars at all, but from cracks in spacetime itself, places where gravity's hidden counterpart briefly leaks into our universe, sparking electromagnetic fireworks. The most tantalizing clue lies in the burst's polarization. The way their radio waves twist as they travel through space. Some FRBs show bizarre, corkscrew-like twists, suggesting they've passed through incredibly strong magnetic fields or warped spacetime. If gravity's shadow twin were subtly bending the fabric of reality around these sources, it could imprint these strange signatures like a fingerprint on light. Whether it's an unseen force tweaking neutron stars or spacetime itself unraveling in pockets, one thing's clear: fast radio burst repeaters aren't just cosmic anomalies, they're potential messengers from the frontier of physics. Every erratic pulse challenges what we know about energy, gravity, and the universe's hidden wiring. And until we decode their riddles, these flickering enigmas will keep broadcasting their secrets across the dark. At the smallest scales imaginable, where particles flicker in and out of existence, and the fabric of spacetime itself trembles, gravity vanishes from the equation. This isn't a metaphor. Quantum mechanics, our most precise theory of the microscopic world, describes three fundamental forces with breathtaking accuracy: electromagnetism, the strong nuclear force, the weak nuclear force. But gravity, it's conspicuously absent, like a guest who never arrived at the party. The equations that predict how electrons orbit atoms or how quarks bind together simply don't account for the force that holds planets in orbit. And when physicists try to stitch gravity into the quantum framework, the math explodes into infinities, rendering the equations useless. This glaring disconnect isn't just a technical hiccup, it's the single greatest unsolved problem in theoretical physics. The heart of the issue lies in gravity's stubborn refusal to play by quantum rules. At the quantum level, forces are carried by particles, photons for electromagnetism, gluons for the strong force. But attempts to pin down gravity's hypothetical particle, the graviton, lead to absurdities. Imagine trying to balance a bowling ball on a toothpick. That's the kind of instability that crops up when gravity is forced into the quantum world. The numbers spiral out of control because gravity, unlike other forces, warps the very stage on which particles perform, spacetime itself. Quantum particles exist in fuzzy, probabilistic clouds, but gravity demands a smooth, deterministic spacetime. It's like trying to mix oil and water. The two simply refuse to blend. This is where gravity's shadow twin could rewrite the script. If gravity operates differently at quantum scales, if it has a hidden counterpart that only reveals itself in these extreme conditions, it might explain why our current theories fail. Picture a lock that won't open because you've been using the wrong key. The real mechanism might require two keys turned simultaneously, one for the gravity we know and another for its quantum counterpart. Some theories, like loop quantum gravity, propose that spacetime itself is granular at the tiniest scales, woven from indivisible loops. Others, like string theory, suggest gravity leaks into extra dimensions, diluting its strength in our observable universe. But the most tantalizing idea, that gravity's shadow twin isn't a particle or a wave, but a fundamental property of information itself. A code written into the fabric of reality that only deciphers under quantum conditions. The implications ripple far beyond theory. If gravity's quantum gap stems from an unseen partner, it could revolutionize technology. Quantum computers, which rely on manipulating particles in superposition, might one day harness gravitational effects we can't yet measure. Black holes, those cosmic paradoxes where quantum and gravitational effects collide, could become laboratories for testing these ideas. Even the birth of the universe, where quantum fluctuations presumably ignited cosmic inflation, might look radically different through this lens. Yet the mystery deepens when we consider experiments. Gravity is so weak at small scales that detecting its quantum effects is like listening for a whisper in a hurricane. Current instruments like gravitational wave detectors aren't sensitive enough, but upcoming projects like space-based interferometers or ultra-precise atomic clocks might finally glimpse gravity's shadow twin in action. Until then, this gap remains a frontier, a silent challenge to our understanding of reality. Whether it's hidden dimensions, granular spacetime, or an entirely new physics waiting to be discovered, one thing's clear: the universe isn't just keeping secrets. It's daring us to look closer. Neutrinos are the universe's most elusive particles, tiny, nearly massless phantoms that slip through entire planets like they're not even there. They outnumber atoms in your body by billions to one, yet detecting a single neutrino takes a detector the size of an Olympic swimming pool. But here's the real puzzle: they do have mass. Just a whisper of it, so faint that for decades physicists assumed they had none at all. The discovery that neutrinos weigh something earned a Nobel Prize, but it also opened a door to one of physics' deepest mysteries: why so little? And could gravity's shadow twin be the invisible hand keeping them nearly weightless? Think of neutrinos as cosmic featherweights. An electron, already one of the lightest particles, is at least 5 million times heavier than the heaviest neutrino. That's like comparing a grain of sand to a freight train. Standard physics struggles to explain this staggering imbalance. In the particle zoo, mass usually comes from interactions with the Higgs field, the invisible energy blanket that gives particles their heft. But neutrinos barely interact with it at all. It's as if they're standing in a downpour yet somehow staying dry. This is where gravity's shadow twin steps into the spotlight. Some theories suggest neutrinos might be influenced by a hidden gravitational force, one that operates on scales so tiny it's undetectable in everyday life. Imagine gravity as a double-layered curtain. The familiar pull we experience is just the outer layer, while beneath it, a subtler force tugs at particles like neutrinos, suppressing their mass. Modified gravity models propose that this secondary influence could act as a cosmic dampener, preventing neutrinos from gaining weight the way other particles do. Then there's the oscillation enigma. Neutrinos don't just exist in one flavor: electron, muon, and tau neutrinos can morph into one another as they travel. a quantum quirk that only makes sense if they have mass. But the math behind these oscillations hints at something stranger. Neutrinos might be seesaw particles, with their feather-like masses balanced by hypothetical heavy counterparts we've yet to detect. If gravity's shadow twin exists, it could be the fulcrum in this cosmic seesaw, tilting the balance to keep neutrinos nearly massless while their heavy twins lurk in realms beyond our current reach. The implications ripple far beyond particle physics. If neutrinos are whispering clues about hidden gravitational forces, they could be the key to unifying quantum mechanics and general relativity, the holy grail of modern physics. Their minuscule masses might even hold answers to why the universe is made of matter at all. Every second, trillions of neutrinos from the sun alone pass through your body, each one a potential messenger from the frontier of known physics. What makes this mystery so electrifying isn't just the particles themselves, it's what they represent. Neutrinos might be the universe's way of winking at us, hinting that gravity's rules aren't just written in the motions of planets and stars, but etched into the fabric of reality at scales we're only beginning to probe. And until we crack their code, these ghostly particles will keep slipping through our fingers, carrying secrets we've yet to grasp. Imagine holding a credit card, smooth plastic on one side, but etched with microscopic grooves on the other that project a shimmering 3D image when light hits them just right. Now take that concept and scale it up to cosmic proportions. The holographic principle suggests our universe might work the same way. All the information contained within its vast volume, every star, planet, and atom, could be encoded on a two-dimensional boundary at its edge, like data pressed onto a cosmic DVD. It's not just a metaphor. This radical idea implies that the 3D reality we experience might be a projection from some deeper, flatter layer of existence. At first glance, this sounds like science fiction, but the math behind it is startlingly precise. Black holes, those ultimate cosmic shredders, present a paradox. They devour information, yet somehow must preserve it, according to quantum mechanics. In the 1990s, physicist Gerard T. Hooft proposed that a black hole's swallowed information isn't destroyed but smeared across its event horizon, the point of no return. Leonard Susskind later expanded this into the holographic principle, arguing that the entire universe might operate similarly. Picture a movie screen. The images appear three-dimensional, but every detail originates from flat pixels. If the universe is a hologram, gravity's shadow twin could be the unseen projector, a hidden force translating 2D data into our 3D experience. Here's where it gets mind-bending. In a holographic universe, gravity wouldn't just be a force, it could be an emergent property, a side effect of how information is encoded and processed at the boundary. Think of it like the pixels on your phone screen creating the illusion of movement. Gravity might be the movement emerging from deeper information dynamics. Modified gravity theories align eerily well with this idea. If gravity's shadow twin exists, it might not operate within our familiar 3D space at all, but at the universe's 2D edges, subtly shaping how reality renders itself inward. The implications ripple through every corner of physics. Quantum entanglement, the spooky connection between particles across vast distances, could be a natural consequence of this holographic framework, with entangled particles linked by underlying 2D data. Even the fabric of spacetime itself might not be fundamental, but a kind of user interface, with gravity's shadow twin serving as the operating system running beneath. Yet the most tantalizing clue lies in the math. Equations describing certain quantum systems without gravity perfectly match those describing gravity in higher dimensions, a duality called the add s/CFT correspondence. It's as if the universe left a breadcrumb trail, hinting that gravity as we know it might just be the tip of a deeper, flatter iceberg. Whether it's black holes whispering their secrets or quantum particles dancing to a hidden code, the holographic principle forces us to confront a staggering possibility. Reality as we perceive it might be the grandest illusion of all. And if gravity's shadow twin is the architect behind this cosmic projection, uncovering its nature wouldn't just solve mysteries, it would redefine what it means to exist. What if gravity isn't a fundamental force at all, but an illusion, a side effect of something far more primal? That's the radical proposition of entropic gravity, a theory that flips everything we thought we knew about the universe's glue on its head. Instead of space-time bending under mass, imagine gravity emerging from chaos itself, the natural tendency of systems to descend into disorder. Picture a crowded room. As people move randomly, they create pressure, pushing others around. In this view, gravity isn't a force transmitted by particles or warped geometry, but the statistical outcome of countless microscopic interactions we can't yet see. The idea traces back to physicist Eric Verland, who in 2010 proposed that gravity might be an entropic force, a byproduct of information scrambling at the universe's most basic level. Think of it like temperature. We feel heat as a macroscopic property, but it's really just the chaotic motion of molecules. Similarly, entropic gravity suggests that what we perceive as attraction between masses is actually spacetime's way of maximizing disorder. It's as if the cosmos is a vast, cosmic game of Tetris, with gravity being the emergent strategy to keep the blocks from piling up. This is where gravity's shadow twin enters the picture. If gravity arises from entropy, could there be a secondary, hidden layer to this process, a deeper informational framework that occasionally leaks into our reality? Modified versions of entropic gravity propose that quantum fluctuations in this underlying structure might produce subtle deviations from Newton's and Einstein's predictions, especially in extreme environments like galaxy cores or the early universe. Imagine a shadowy undercurrent beneath the entropic tide, tweaking gravity's strength where the math falls short. The implications are staggering. Entropic gravity could explain dark matter without invoking invisible particles. Instead, the extra gravitational pull we attribute to dark matter might stem from how entropy organizes itself on galactic scales. It's like realizing the missing money in your budget was hiding in plain sight, just accounted for differently. But the theory's real power lies in its potential to bridge quantum mechanics and general relativity. If gravity is entropic, it doesn't need quantizing. It's already rooted in the statistical behavior of quantum bits. Yet challenges remain. Entropic gravity struggles to explain phenomena like gravitational waves or the precise orbits of binary pulsars without additional tweaks. Critics argue it's more a provocative framework than a finished theory, but that's what makes it so exciting. It's a door cracked open to a new way of seeing reality. Whether it's right or wrong, entropic gravity forces us to ask, what if we've been mistaking the effect for the cause all along? And if gravity's shadow twin is lurking in the math, it might be the key to unlocking a universe where even the most familiar forces are stranger than we dreamed. The universe isn't just expanding, it's accelerating, as if some unseen hand is pressing harder on the cosmic gas pedal with each passing moment. Scientists call this mysterious force dark energy, and it makes up nearly 70% of the universe's total energy budget. Yet despite its dominance, we have no idea what it actually is. The leading theory pins it on the cosmological constant, a sort of background energy woven into spacetime itself, but the numbers don't add up. Quantum mechanics predicts this energy should be a staggering 120 orders of magnitude stronger than what we observe. That's like expecting a hurricane and feeling only a faint breeze. This colossal mismatch suggests something fundamental is missing from our equations, perhaps gravity's shadow twin, quietly tempering or amplifying dark energy's effects behind the scenes. Consider the cosmic tug of war playing out on the grandest scale. On one side, dark energy pushes galaxies apart, stretching the fabric of space itself. On the other, gravity, both the familiar kind and its hypothetical shadow counterpart, pulls matter together in a silent battle for the universe's fate. For billions of years, gravity held the upper hand, slowing the expansion. But around 5 billion years ago, dark energy gained the advantage, and the universe began accelerating. The odd part, this timing coincides roughly with the emergence of large-scale cosmic structures. Could there be a hidden link between the rise of dark energy's dominance and gravity's shadow twin stepping back, like a cosmic seesaw tilting toward expansion? Modified gravity theories offer a provocative alternative. What if dark energy isn't a separate force at all, but a symptom of gravity behaving differently on cosmic scales? Picture a rubber band that weakens when stretched too far, except in this case, the rubber band is space-time, and the weakening mimics the effect of an anti-gravitational push. Some models suggest gravity's shadow twin could act as a dimmer switch, subtly reducing gravity's grip in the vast emptiness between galaxies, creating the illusion of dark energy's repulsive force. It's like realizing the wind pushing your car forward was actually the brakes loosening all along. Yet the plot thickens when we examine the universe's geometry. Precise measurements of the cosmic microwave background reveal a universe that's flat to an astonishing degree, a delicate balance that requires dark energy's exact value to avoid collapsing or tearing apart. If gravity's shadow twin is in the mix, tweaking the strength of attraction or repulsion, it could explain this fine-tuning. Imagine a watchmaker adjusting two hidden gears to keep perfect time, one visible, one unseen, working in tandem to maintain cosmic equilibrium. The stakes couldn't be higher. If dark energy's acceleration continues unchecked, the universe could end in a big rip where even atoms are torn apart. But if gravity's shadow twin is silently counteracting it, the cosmos might find a more graceful exit. Every supernova measured, every galaxy cluster mapped, brings us closer to unraveling this enigma. Whether it's an unknown energy or gravity's hidden counterpart, one thing's certain: the universe's expansion is hiding a secret, and the answer might rewrite not just our fate, but the very laws we thought governed reality. When the Event Horizon Telescope unveiled humanity's first image of a black hole in 2019, it wasn't just a triumph of technology, it was a cosmic Rorschach test. The now iconic golden ring of light surrounding the abyss of M87's supermassive black hole matched Einstein's predictions eerily well, but zoom in closer and the details get strange. The ring's brightness isn't uniform, it's lumpy, asymmetrical, as if something is warping the light in ways general relativity alone can't explain. This isn't just an optical quirk, it might be the signature of gravity's shadow twin subtly bending the rules at the universe's most extreme edge. Take the ring's unexpected thinness. Simulations based on standard physics predicted a thicker, more diffuse glow, yet the real image shows a razor-sharp silhouette. It's like expecting a candle's hazy aura but seeing the stark outline of a flashlight beam instead. One possible explanation: an additional gravitational influence magnifying the light's path just enough to sharpen the edges. Picture a funhouse mirror with a hidden curvature, one that doesn't just distort reflections but focuses them. If gravity's shadow twin operates near black holes, it could act like that hidden lens, tweaking spacetime's geometry to produce a crisper shadow than Einstein's equations alone would allow. Then there's the brightness asymmetry. The ring's southern region shines noticeably brighter than the north, a discrepancy that goes beyond the Doppler effect caused by the black hole's spin. Some researchers suggest this could hint at an uneven gravitational field, like a hidden weight tugging at spacetime from an angle we can't directly observe. Modified gravity theories propose that in the presence of extreme curvature, an unseen component of gravity might amplify or dampen light in unpredictable ways. Imagine waves crashing against a rocky shore, only to encounter an invisible sandbar that redirects their energy. That's the kind of subtle interference that could be at play here. The most tantalizing clue lies in the shadow's size. According to general relativity, a black hole's shadow should scale neatly with its mass. But what if gravity's shadow twin slightly alters that relationship in extreme environments? Tiny deviations in the shadow's diameter could reveal where standard models fail and where a hidden gravitational influence takes over. It's like stepping on a scale and finding you weigh slightly less than expected, not because you've lost mass, but because gravity itself is playing by different rules in that moment. What makes these anomalies so electrifying isn't just their existence, it's their implications. If black holes, the ultimate laboratories for testing gravity, show features that defy our models, it means we're missing a piece of the puzzle. Whether it's an unseen facet of gravity or something entirely new, the Event Horizon Telescope didn't just capture a black hole's shadow. It might have glimpsed the silhouette of a deeper truth. And as sharper images emerge from future observations, these cosmic fingerprints could lead us to the next revolution in physics. Neutron stars are the universe's most precise timekeepers, cosmic lighthouses spinning with such regularity that their pulses rival atomic clocks. But every so often, these celestial metronomes stutter. Without warning, a pulsar's rotation speeds up by a fraction of a second, as if an unseen hand gave it a sudden, forceful nudge. Astronomers call these events glitches, and they're among the most perplexing behaviors in astrophysics. The craziest part, these speed-ups shouldn't be possible. Neutron stars are so dense that a teaspoon of their material weighs 1 billion tons, making them nearly impervious to external forces. Yet something is reaching inside these ultra-stable objects and tweaking their spin, something we can't yet explain. Take the Vela pulsar, one of the most notorious glitches in the galaxy. Every few years, it suddenly spins faster, gaining speed in a blink before settling back into its usual rhythm. Traditional explanations point to starquakes, cracks in the neutron star's rigid crust that momentarily shrink its radius, like a figure skater pulling in their arms to spin faster. But here's the problem. The energy released in these glitches often dwarfs what starquakes alone could produce. It's like expecting a pebble to trigger an avalanche. The scales don't match. This is where gravity's shadow twin enters the scene. Neutron stars aren't just dense. Their cores might harbor exotic states of matter, hyperfluid neutrons, free-floating quarks, or even stranger particles. If an unseen gravitational force interacts with these extreme materials, it could destabilize the star's interior just enough to trigger a glitch. Picture a spoon stirring a cup of coffee. Normally, the liquid moves predictably, but if the spoon suddenly changes shape, the swirls become chaotic. Similarly, gravity's shadow twin might subtly alter how the neutron star's core rotates, transferring momentum to the crust in bursts we observe as glitches. Modified gravity theories suggest that under such immense pressures millions of times greater than Earth's core gravity's rules might shift. Normally, a neutron star's crust and core rotate in sync, locked together by magnetic fields and friction. But if gravity's shadow twin weakens this coupling in sporadic pulses, the core could briefly outpace the crust, then snap back into alignment, releasing pent-up energy like a wound-up spring. It's a cosmic version of the stick-slip effect that causes earthquakes, only here the slip might be governed by physics we've yet to describe. The implications ripple beyond neutron stars. If glitches reveal an unseen gravitational influence, they could offer clues about dark matter's behavior in extreme environments, or even hint at extra dimensions crumpled at microscopic scales. Every time a pulsar stutters, it's not just a fluke. It's a message, a flicker of insight into forces operating where standard physics falls silent. And until we decode these cosmic hiccups, neutron stars will keep spinning their mysteries into the void, one glitch at a time. Galaxies aren't supposed to defy the rules, especially not one as fundamental as dark matter. Enter NGC 1052 DF2, a cosmic rebel that flips the script entirely. This ghostly galaxy, floating 65 million light-years away, spins so slowly that its visible stars alone account for nearly all its gravity. No hidden mass, no mysterious dark matter halo, just ordinary starlight holding everything together. It's like finding a skyscraper standing tall without a foundation, defying every architectural law we know. The discovery sent shockwaves through astrophysics. Dark matter isn't just a theoretical crutch, it's the invisible scaffolding thought to underpin all galaxies, shaping their rotation and structure. Yet here's DF2 operating perfectly fine without it. Its stars move at a leisurely pace, their velocity so low that if dark matter were present, we'd see their orbits warp dramatically. Instead, they cruise along as if gravity's usual rules have been quietly rewritten. This is where gravity's shadow twin steps into the spotlight. If an unseen gravitational influence were at work, one that mimics dark matter's effects in most galaxies but switches off in environments like DF2, it could explain this cosmic anomaly. Picture a universal dial that adjusts gravity's strength based on context, cranked up in galaxy clusters where dark matter seems abundant, but dialed down in sparse, diffuse galaxies like this one. Modified gravity theories such as MOND suggest that in regions with extremely weak gravitational fields, the rules might shift, eliminating the need for dark matter entirely. But DF2 isn't just an isolated oddity. Its sibling, DF4, exhibits similar dark matter-free behavior, hinting at a pattern rather than a fluke. Even stranger, these galaxies are too pristine, lacking not just dark matter, but also the dense central bulges and spiral arms typical of their peers. It's as if they formed in a parallel universe where the usual cosmic ingredients were left out of the recipe. Critics argue these galaxies might have had their dark matter stripped away by violent collisions or tidal forces, but the evidence is thin. DF2 shows no scars of past trauma, no signs of a gravitational mugging that could explain its missing mass. Others suggest it's a failed galaxy, one that never accumulated dark matter to begin with, a cosmic underachiever born in a pocket of the universe where the dark matter lottery wasn't won. The implications are staggering. If galaxies can exist without dark matter, it challenges the very foundation of modern cosmology. Either dark matter isn't as universal as we thought, or gravity itself is more flexible, a chameleon force that adapts to its environment. DF2 forces us to confront an uncomfortable truth. Our cosmic models might be missing a variable, one that's been hiding in plain sight. Whether it's gravity's shadow twin or a flaw in our dark matter narrative, this galactic rebel isn't just an outlier, it's a beacon, illuminating the edge of our understanding and daring us to look beyond it. The universe isn't just a scattering of galaxies, it's a masterpiece of architecture woven together by vast, shimmering threads of gas and dark matter known as cosmic filaments. These colossal tendrils stretch hundreds of millions of light-years, forming the backbone of the cosmic web, the largest structure in existence. Galaxies cling to them like pearls on a necklace, drawn together by gravity's invisible hand. But here's the puzzle: these filaments shouldn't be as stable as they are. The gas threading through them is so diffuse, so thinly spread, that even the faintest turbulence should tear them apart. Yet they persist, enduring for billions of years as if held together by some unbreakable cosmic glue. Take the massive filament connecting the Able 222 and Able 223 galaxy clusters, a river of hot gas nearly 60 million light-years long. Simulations predict such structures should fray and dissipate over time, their contents scattering into the void. Instead, this filament remains intact, a glowing highway in the darkness. The math suggests gravity from visible matter alone can't account for its resilience. So what's keeping it from unraveling? One tantalizing possibility is gravity's shadow twin, a secondary gravitational influence reinforcing these delicate threads from within. Imagine a spiderweb reinforced with invisible strands, each one too fine to see yet strong enough to hold the whole structure together. That's the kind of subtle support some researchers propose might be at work in the cosmic web. Modified gravity theories suggest that in environments where matter is stretched thin like these sprawling filaments, gravity's hidden counterpart could kick in, providing just enough extra pull to stabilize the gas against disruption. It wouldn't take much. A fractional increase in gravitational strength at these scales could be the difference between a filament holding firm or dissolving into chaos. But the mystery deepens when we examine the filament's temperatures. Many of these gaseous threads are far hotter than expected, glowing with X-rays that betray the presence of energy sources we can't yet pinpoint. Some astronomers speculate this heat could come from shock waves rippling through the gas, stirred by the motion of galaxies or the collapse of dark matter halos. Others wonder if gravity's shadow twin might be indirectly heating the filaments, like an unseen hand stirring a pot of cosmic soup. If this hidden force interacts weakly with the gas, it could transfer energy in ways that don't show up in standard models, leaving only the heat as a clue to its presence. The cosmic web isn't just a curiosity, it's a living blueprint of the universe's growth, a fossil record of how gravity shaped everything we see. And if its filaments are being bolstered by an unseen force, it would mean our understanding of structure formation is missing a critical variable. Whether it's dark matter's hidden dynamics or gravity's secret twin quietly tightening the stitches of the cosmic tapestry, one thing's clear: the universe's grand design holds secrets we've only begun to trace. And every thread we follow leads deeper into the unknown. Time isn't as constant as it seems. Take two identical atomic clocks, one placed on Earth's surface, the other launched into orbit. Over months, the orbiting clock ticks slightly faster, gaining microseconds against its grounded twin. This isn't a mechanical flaw, it's Einstein's general relativity in action. Gravity warps time itself, slowing its flow wherever the gravitational pull is stronger. But what happens when clocks in identical gravitational fields tick at different rates? That's the enigma scientists face when studying time dilation anomalies, tiny deviations that hint at something beyond Einstein's equations. Consider the gravity probe experiment in 1976, where a hydrogen maser clock flown to 10,000 kilometers matched predictions to within 1% except for a faint, unexplained discrepancy. Or the decades of GPS satellite data revealing that even after accounting for Earth's gravity and orbital motion, some timing residuals stubbornly resist explanation. These aren't measurement errors, they're consistent, repeatable glitches in time's fabric. This is where gravity's shadow twin enters the scene. If an unseen gravitational influence subtly alters how space-time curves in extreme conditions, it could tweak time dilation in ways that defy standard models. Picture a river flowing downhill. Gravity's familiar pull is the slope, but hidden currents beneath the surface might speed or slow the water unpredictably. Modified gravity theories propose that in regions of intense gravitational strain near black holes or neutron stars, this secondary force could warp time's flow just enough to leave fingerprints in precise clock measurements. The most tantalizing clues come from pulsars. These ultra-precise cosmic clocks should slow predictably as they emit energy, but some exhibit timing glitches that can't be blamed on starquakes or magnetic shifts alone. Their pulses arrive milliseconds early or late, as if time itself stutters in their vicinity. Could this be gravity's shadow twin flickering in and out of sync with the main force? Laboratory experiments are now chasing these anomalies. Optical lattice clocks, accurate to within 1 second over 15 billion years, are placed in varying gravitational potentials mounted on towers, submerged underground, to hunt for deviations. Early results suggest whispers of something odd. Time might not dilate exactly as predicted when gravity is neither extremely strong nor weak, but in transitional zones. It's as if the universe has a hidden tempo, one that only becomes audible when we listen at the edge of precision. Whether these discrepancies point to new physics or merely finer layers of relativity's tapestry, one thing's certain: time isn't just bending to gravity's will, it's whispering secrets about forces we've yet to name. And every anomalous tick of the clock brings us closer to hearing them. Black holes devour everything, even light. But what if the universe has cosmic fountains that do the opposite? Enter white holes, the theoretical yin to black holes' yang. While black holes pull matter in past the point of no return, white holes would violently expel it, spewing energy and particles outward with such force that nothing could ever enter. It's like a one-way door swinging open only to push, never to pull. General relativity allows for such objects mathematically, but proving their existence is another matter. No confirmed white hole has ever been observed, leaving them floating in the realm of tantalizing speculation. Yet the idea isn't pure fantasy. Einstein's equations are symmetric. They don't care if time runs forward or backward. Flip a black hole's math in reverse, and you get a white hole. A singularity that only emits, never absorbs. Some theorists suggest these cosmic exhaust vents could be the other end of black hole tunnels, ejecting matter that fell in elsewhere. Picture a drain pipe where water vanishes down one end only to gush out the other. But here's the twist: white holes couldn't form naturally in our universe's timeline. They'd need to exist from the very beginning, like pre-installed cosmic fire hydrants, or arise from some extreme gravitational rebound, a black hole's death throes, perhaps, or a collision with another universe. This is where gravity's shadow twin enters the conversation. If an unseen gravitational force exists, one that operates under different rules in extreme conditions, it might provide the mechanism white holes need to stabilize. Imagine a black hole's crushing gravity meeting resistance from a hidden counterpart, like two hands pressing against each other until the pressure forces an eruption. Modified gravity theories hint that under such strain, space-time might reconfigure itself, birthing a white hole as a release valve. It's a cosmic pressure cooker with gravity's shadow twin turning the dial. The implications ripple beyond theory. If white holes exist, they could explain mysterious cosmic explosions with no clear source gamma-ray bursts that appear too energetic, too sudden, to fit known stellar processes. Some researchers even speculate that the Big Bang itself could have been a primordial white hole, a single point disgorging the entire universe in a fiery exhale. But the real challenge is detection. White holes would shine brilliantly, yet their signatures would mimic other astrophysical phenomena, hyperactive quasars, supernova on steroids, or even dark matter annihilations. Telling them apart would require spotting a pattern, an outflow too perfect, too symmetrical to be anything else. Until then, white holes remain ghosts in the equations, cosmic mirages that tantalize with their possibility. Whether they are hiding in plain sight or confined to chalkboard speculation, one thing's certain: the universe loves balance, and if black holes exist, their opposites might be waiting in the shadows, or rather, blasting light into them. Gravitational waves are supposed to be clean, crisp signals, ripples in spacetime from cataclysmic events like black hole mergers, ringing out once before fading into silence. But some detectors have picked up something stranger, faint echoes trailing the main signal like cosmic afterthoughts. These whispers arrive microseconds after the primary wave, as if spacetime itself is bouncing the signal back to us through some unseen medium. It's the equivalent of shouting into a canyon and hearing your voice return not once, but twice, except in this case, the canyon is the fabric of the universe, and the second echo shouldn't exist. The first hints of these echoes emerged in 2016, when researchers reanalyzing LIGO groundbreaking detection of merging black holes noticed anomalous bumps in the data. At first, they were dismissed as noise glitches in the detector's sensitive instrumentation, but as more collisions were recorded, the pattern persisted. In a handful of events, the gravitational wave signal didn't just peak and decay, it flickered as if something was distorting its path, the odds of this being random interference. Less than 1 in 200, that's when physicists began to wonder, what if these echoes aren't artifacts but clues? One radical explanation points to quantum gravity effects near black hole event horizons, a realm where Einstein's smooth spacetime might shatter into a froth of microscopic fluctuations. Imagine tossing a stone into a pond. Normally, the ripples spread outward evenly, but if the pond's surface were covered in a lattice of tiny obstacles, the waves would scatter, creating secondary patterns. In this analogy, the obstacles are quantum-scale structures at the edge of a black hole, and the echoes are the gravitational waves ricocheting off them. But here's where gravity's shadow twin enters the picture. If an unseen gravitational force interacts with spacetime in ways we can't yet measure, it might leave fingerprints in these echoes. Picture a hall of mirrors where one mirror is invisible. You wouldn't see it, but you'd notice the extra reflections. Similarly, gravity's shadow twin could be warping spacetime just enough to create these delayed signals, a cosmic echo chamber operating beyond our current models. Critics argue the echoes could still be systematic noise vibrations in LIGO mirrors or quantum fluctuations in the lasers themselves. But proponents counter that the timing of these anomalies is too precise, too consistent with theoretical predictions of quantum gravitational effects. The debate rages on, but one thing's certain: if these echoes are real, they're not just curiosities. They're cracks in the foundation of general relativity, hints that black holes might have structures or quantum hair that standard physics says they shouldn't. Future detectors like the space-based LISA observatory or next-generation ground-based arrays could settle the controversy. With greater sensitivity, they'll either confirm these echoes as noise or unveil them as the first tremors of a gravitational revolution. Until then, these faint whispers linger at the edge of detection, teasing us with the possibility that every black hole collision isn't just a death knell, but a message reverberating through dimensions we've yet to comprehend. Dark matter isn't just missing in some galaxies, it's overabundant in others, lingering where it shouldn't be like an uninvited cosmic guest. Take Galaxy Cluster Able 521, where the gravitational pull suggests twice as much dark matter as standard models predict. It's as if the universe spilled extra invisible mass into this corner of space, defying every expectation of how dark matter should distribute itself. These phantom dark matter hotspots aren't just statistical flukes, they're systematic anomalies clustered in ways that challenge our understanding of gravity's rules. The puzzle deepens when we examine how this excess manifests. In these regions, gravitational lensing, the bending of light around massive objects, reveals distortions too strong for the visible matter present. Yet the dark matter's distribution doesn't match simulations of how it should clump. Instead of forming smooth halos around galaxies, it pools in peculiar, asymmetrical blobs, as if tugged by an unseen force. Some researchers speculate this could be gravity's shadow twin at work, a secondary influence amplifying dark matter's effects in specific locales. Picture a magnifying glass warping sunlight into a scorching point. This hidden gravitational layer might be concentrating dark matter's pull in erratic, unpredictable ways. Modified gravity theories offer a provocative twist. What if the extra dark matter isn't matter at all, but a signpost of gravity behaving differently under certain conditions? In places where visible matter is densely packed, like galaxy cluster cores, gravity's shadow twin could kick in, mimicking the effects of additional mass. It's like stepping on a scale and seeing your weight double, not because you've gained mass, but because gravity's strength secretly spiked. This wouldn't just explain phantom dark matter, it could rewrite how we map the universe's hidden scaffolding. Yet the anomalies resist easy categorization. Some overabundant dark matter galaxies, like Dragonfly 44, are ultra-diffuse, so sparse they shouldn't host such massive halos. Others, like the Bullet cluster's dark matter, Bullet, show concentrations that trail behind visible matter, as if dragged by an invisible leash. If gravity's shadow twin is real, its fingerprints might lie in these asymmetries, subtly altering how dark matter clumps or disperses in ways our models can't yet replicate. The stakes are cosmic. If phantom dark matter reveals a hidden facet of gravity, it could mean dark matter itself is more dynamic or even interactive than we thought. Perhaps particles collide, decay, or transform in regions where gravity's rules bend. Or perhaps the universe is more mischievous than we imagined, scattering clues that force us to question whether we've been misreading its deepest language all along. Either way, these enigmatic excesses aren't just outliers, they're cosmic breadcrumbs leading us toward a truth far stranger than we've dared to suppose. The vacuum of space isn't empty. It's a seething quantum foam, bubbling with particles flickering in and out of existence so fast we can't detect them directly. This quantum jitter isn't just theoretical noise, it carries real energy, a background hum woven into the fabric of reality itself. Physicists call it vacuum energy, and according to quantum field theory, it should be unimaginably strong, enough to warp spacetime on cosmic scales. Here's the problem: when we calculate its expected strength using quantum mechanics, the numbers are catastrophically wrong. Not just off by a little, wrong by a factor of 10 to the power of 120. That's like predicting a candle's glow and instead getting a supernova. This glaring mismatch, known as the vacuum catastrophe, isn't just a minor hiccup in physics. It's the largest discrepancy between theory and observation in all of science. So where's the disconnect? Quantum mechanics treats vacuum energy as the sum of all possible particle fluctuations, a cacophony of virtual particles popping in and out of existence. The math suggests this should create a gravitational effect so powerful it would rip the universe apart. Yet when we measure the actual curvature of space-time, through the universe's expansion or the cosmic microwave background, the vacuum energy is almost negligible. It's as if the universe has a hidden dimmer switch, turning down the volume on quantum chaos just enough to keep reality intact. This is where gravity's shadow twin enters the stage. What if an unseen gravitational influence counteracts or fine-tunes vacuum energy behind the scenes? Picture a cosmic balancing act. On one side, quantum fluctuations push spacetime outward with unimaginable force. On the other, gravity's hidden counterpart pulls back, neutralizing the effect. Modified gravity theories propose that in the presence of extreme energy densities like those in the quantum vacuum, a secondary gravitational field might activate, acting as a stabilizer. Imagine two dancers perfectly matched in strength, their opposing forces canceling out to create the illusion of stillness. The implications are staggering. If gravity's shadow twin regulates vacuum energy, it could explain why the cosmological constant the term Einstein introduced to represent this energy is so finely tuned. Too much and galaxies would never form, too little and the universe would collapse. This delicate balance suggests something deeper at work, not random chance, but a hidden mechanism keeping reality in equilibrium. Some theorists even speculate that this could be a clue to quantum gravity, the missing link between Einstein's relativity and the quantum world. Yet the mystery deepens when we consider alternatives. Could vacuum energy be screened by some unknown particle or field, its effects localized rather than cosmic? Or might the quantum fluctuations we're summing up include canceling terms we haven't yet discovered? The vacuum catastrophe isn't just an embarrassment, it's a beacon, illuminating the edge of our understanding. Whether it's gravity's shadow twin quietly adjusting the dials or an entirely new physics waiting to be uncovered, one thing's clear: the empty space around us is anything but simple. And until we crack its code, the universe will keep its most explosive secret hidden in plain sight. Black holes don't just swallow matter. They erase information, shredding the very essence of what falls in beyond recovery. Or do they? A radical idea is gaining traction. Black holes might not be cosmic shredders after all, but more like cosmic sieves, subtly letting information slip back out into the universe. This isn't some sci-fi fantasy. It's a serious proposal to resolve one of physics' most vexing paradoxes, and gravity's shadow twin could be the missing piece of the puzzle. Imagine tossing a book into a fireplace. The pages burn, the ink vanishes, but if you could somehow capture every photon of light, every wisp of smoke, you could theoretically reconstruct the book's contents. That's the principle behind quantum mechanics. Information is never truly lost, just scrambled. But black holes, with their monstrous gravity, seem to break this rule. Once something crosses the event horizon, it's gone for good, or so we thought. The black hole information paradox pits quantum mechanics against general relativity in a battle with no clear winner. Unless, of course, information isn't vanishing at all. It's just escaping in ways we haven't yet detected. Enter the concept of information echoes. Some theorists propose that black holes don't just emit random Hawking radiation. They subtly encode information within it, like a faint watermark on light. This wouldn't be obvious. It would require gravity to operate with a precision we've never observed, tweaking the radiation's properties in infinitesimal ways. But here's where gravity's shadow twin comes in. If an unseen gravitational influence interacts with spacetime at the quantum level, it could act as a cosmic scribe, imprinting the lost information onto outgoing radiation. Picture a black hole not as a one-way trap, but as a tangled labyrinth where the walls themselves whisper secrets to particles fleeing its grasp. The mechanism might hinge on quantum entanglement, the spooky connection between particles that persists across vast distances. As a black hole evaporates, the particles it emits could remain entangled with the information trapped inside, creating a bridge between the interior and the outside world. Gravity's shadow twin might mediate this process, ensuring the information isn't lost but transferred, like a relay runner passing a baton. It's a delicate dance, one that would require gravity to have a hidden layer of complexity we've yet to map. The implications are staggering. If black holes preserve information, it would mean our understanding of space-time is incomplete, missing a crucial channel through which data flows. It would also suggest that gravity isn't just a force, it's a cryptographic system, silently encoding the universe's history in ways we're only beginning to decipher. Future experiments, like more precise measurements of Hawking radiation or quantum simulations of black hole analogs, might finally catch these echoes in the act. Until then, the paradox remains a cosmic riddle written in the very fabric of reality, waiting for its solution to emerge from the shadows. Orbits are supposed to be gravity's signature, predictable paths carved by the relentless pull of mass. But scattered across the cosmos, there are rebels, celestial bodies tracing loops and spirals that make no sense under Newton's laws. Take the star S2, whipping around the Milky Way's central black hole at blistering speeds. Its path isn't a tidy ellipse, it's a rosette, a looping flower petal pattern that Einstein's relativity partly explains but not perfectly. Then there's the pioneer Anomaly, where spacecraft drifted off course by fractions of a millimeter per second, as if nudged by an unseen hand. These aren't mere glitches, they're cosmic breadcrumbs hinting that gravity's rulebook might have missing pages. Consider the case of Oumuamua, the interstellar visitor that zipped through our solar system in 2017. Not only did it accelerate unexpectedly as it departed, defying the sun's gravitational grip, but its trajectory didn't match any known comet or asteroid's behavior. Traditional explanations like outgassing fell short. Its path suggested something subtler at work, perhaps a faint but persistent force tweaking its course, something beyond our current models. Could this be gravity's shadow twin, flexing its influence where the primary force wanes? Modified gravity theories propose that under extreme conditions, like an object hurtling through interstellar space, an unseen gravitational layer might emerge, bending motion in ways that look like magic until you account for the hidden variable. The most tantalizing clues come from binary pulsars. These ultra-dense stellar corpses orbit each other with such precision that their timing can be predicted down to microseconds. Yet some, like Quasar B 1913+16, show orbital decay rates that deviate ever so slightly from general relativity's predictions. It's as if an invisible finger is pressing on the scales, altering the dance ever so slightly. One explanation, a secondary gravitational interaction that kicks in at extreme densities or velocities, like a harmonic resonance amplifying certain motions while dampening others. Picture two pendulums swinging in sync until an unseen magnet subtly alters their rhythm. What makes these non-Newtonian orbits so electrifying isn't just their defiance, it's their specificity. They're not random deviations, they're consistent, measurable anomalies that stack up like clues in a cosmic detective story. Whether it's a hidden dimension warping space-time locally or gravity's shadow twin adding a whisper of extra pull where we least expect it, one thing's clear: the universe loves to surprise us. And every odd orbit is a silent challenge, daring us to look deeper and rewrite the rules we thought we knew. Beneath the smooth fabric of space-time we observe lies a seething, chaotic underworld, a realm so tiny it makes atoms look like planets. This is quantum foam, where space-time itself churns with violent fluctuations, bubbling with virtual particles that flicker in and out of existence faster than we can measure. Picture an ocean during a storm. From a distance, the surface appears calm, but up close, it's a frenzy of colliding waves and whirlpools. That's the hidden turbulence of the quantum foam, where space-time isn't just curved, it's boiling. These aren't mere mathematical abstractions. At scales a billion trillion times smaller than an atom, space-time may lose its smooth continuity altogether, fragmenting into a frothy, probabilistic maze. Here, the very concepts of here and now break down, replaced by a seething dance of uncertainty. And within this chaos, some physicists suspect gravity's shadow twin could be stirring, a secondary force emerging from the foam's turbulence like a whirlpool rising from choppy waters. The clues lie in the extreme energy of these fluctuations. According to quantum mechanics, empty space isn't empty at all. It's a maelstrom of particle-antiparticle pairs constantly forming and annihilating. These fleeting disturbances warp space-time on microscopic scales, creating fleeting gravitational ripples. Normally, these cancel each other out, leaving no net effect. But what if, in the foam's most violent eddies, they briefly align, amplifying gravity's influence in ways our equations don't yet capture? It's like a crowd murmuring in a stadium usually. The noise blends into white noise, but occasionally, a synchronized chant erupts, impossible to ignore. This idea gains traction when we examine black holes. At their event horizons, where gravity bends space-time to its breaking point, quantum foam effects should be magnified. Some theories suggest that as matter falls into a black hole, the foam's turbulence could record information about the infalling particles, not on the horizon's surface, as holographic principles propose, but within the foam itself. Gravity's shadow twin might be the mechanism behind this encoding, a hidden hand sculpting spacetime's chaos into a subtle, retrievable pattern. Yet the quantum foam's most tantalizing implication isn't just about gravity, it's about dimensionality. String theory suggests the foam might harbor crumpled-up extra dimensions, too tiny to detect directly but large enough to influence gravity's behavior. Imagine a sponge soaked with water. From afar, it looks solid, but up close, it's riddled with hidden pockets. Similarly, these folded dimensions could be filtering gravity's strength, making it seem weaker in our observable universe while its full force leaks into unseen realms. The challenge: we can't yet probe these scales experimentally. Current particle colliders operate at energies trillions of times too low to directly observe quantum foam. But nature might have left us indirect clues. Cosmic rays, ultra-high-energy particles from deep space, occasionally strike Earth's atmosphere with forces that hint at spacetime's granularity. Some models even propose that if we could measure the foam's fluctuations precisely enough, we'd find slight variations in the speed of light across different wavelengths, a telltale sign of spacetime's turbulent foundation. Whether it's hidden dimensions, emergent gravity, or a cosmic ledger for lost information, the quantum foam represents the final frontier of spacetime's architecture. And until we can peer deeper into its frothy depths, gravity's shadow twin will remain a ghost in the machine, whispering its secrets just beyond the edge of perception. Dark matter doesn't just hide in the shadows. It might be whispering to us through a messenger we've yet to detect. Enter the dark photon, a hypothetical particle that could be the missing link between the invisible cosmos and the forces we know. Unlike ordinary photons, which carry electromagnetic energy and light up the universe, dark photons would operate in a hidden sector, mediating interactions between dark matter particles the way light bridges charged particles in our visible world. But here's the twist: this elusive force carrier might not just connect dark matter to itself, it could be the thread tying it to gravity's shadow twin. Imagine gravity as a river flowing through the universe, shaping galaxies and bending light. Now picture a second current running beneath it, invisible but just as potent, tugging at matter in ways we can't directly see. The dark photon could be the ripple connecting these two streams, a bridge between the familiar pull of gravity and the unseen influence of its shadowy counterpart. Some theories suggest that if dark photons exist, they might occasionally mix with ordinary photons, creating faint, detectable signals like a radio tuned just slightly off-channel, picking up whispers of a hidden broadcast. The evidence is tantalizing but indirect. In particle colliders, certain anomalies, unexpected energy losses, or particle decays hint at something slipping through the cracks of our detectors. Experiments like the Large Hadron Colliders, hidden sector searches, and underground detectors like Xenon 1T have reported anomalies that could align with dark photon interactions. Even cosmic observations, like the excessive positron emission detected by the Alpha Magnetic Spectrometer aboard the International Space Station, might find an explanation in these shadowy particles. But the real intrigue lies in the possibility that dark photons don't just ferry forces between dark matter particles. They might also interact weakly with gravity itself. Modified gravity theories propose that if gravity has a shadow twin, the dark photon could be its emissary, subtly altering how gravity behaves in extreme environments. Picture a magnet wrapped in a thin cloth. The cloth doesn't stop the magnetism, but it changes how it interacts with the world. Similarly, dark photons might dress gravity's shadow twin, filtering its effects in ways that explain cosmic anomalies from galaxy rotations to the clustering of massive structures. Critics argue that the dark photon remains speculative, with no definitive proof yet, but its potential to unify mysteries from dark matter's grip on galaxies to gravity's shadowy quirks makes it a compelling frontier. If discovered, it wouldn't just be another particle. It would be a key to a hidden layer of reality, one where the forces we know are just the surface of something far richer. Until then, the hunt for this ghostly messenger continues, a reminder that the universe's greatest secrets might be written in a language we're only beginning to decipher. The universe appears smooth, planets glide through space, light travels uninterrupted, and the fabric of reality seems seamless. But what if, beneath this polished surface, space-time itself is pixelated, like a digital image zoomed in too far? Detectors designed to measure the most delicate gravitational waves have occasionally picked up something unexpected. A faint, staticky crackle in the data, an anomaly scientists call holographic noise. These aren't instrument glitches or cosmic interference, they're consistent, repeatable signals suggesting that space-time might not be perfectly continuous after all. Instead, it could be composed of unimaginably tiny pixels, fundamental units of reality so small that they only reveal themselves in the quietest, most precise experiments. This granularity isn't just a curiosity, it's a potential window into gravity's shadow twin. Imagine shaking a sheet to dislodge dust. The larger ripples represent the gravity we know, while the fine, almost imperceptible tremors could be the fingerprints of a secondary force. Some theories propose that these space-time pixels aren't random but organized by an underlying structure, like the grid of a hologram. In this view, the 3D universe we experience might be a projection from a 2D boundary, with gravity's shadow twin acting as the unseen encoder, translating flat data into our volumetric reality. The GEO 600 gravitational wave detector in Germany first stumbled onto this noise in the early 2000s. While searching for ripples from distant black holes, the team noticed a persistent, low-level hiss that couldn't be explained by thermal fluctuations or mechanical vibrations. Intriguingly, this noise matched predictions made years earlier by physicist Craig Hogan, who argued that if spacetime has a fundamental resolution, like the grain of a photograph, it should generate detectable jitter at extreme scales. The implications are staggering. We might be sensing the universe's quantum foam, the turbulent seething of spacetime at the Planck scale, where gravity's rules break down and new physics takes over. But here's where it gets even stranger. This noise doesn't behave like typical quantum fluctuations. It's too coherent, too structured, as if something is orchestrating the pixelation. Modified gravity models suggest that gravity's shadow twin could be the hidden conductor, subtly shaping how spacetime's granularity manifests. Picture a theater where the stage appears solid, but the floorboards are actually a series of tiny, moving panels. The actors' particles, light, even black holes perform seamlessly, unaware that beneath them, the structure is dynamic, adjusting in ways that only the most sensitive instruments can detect. The holographic principle adds another layer. If the universe is indeed a hologram, then the noise might be the static of the projector, the faint buzz of information being translated from a lower dimensional surface. In this scenario, gravity's shadow twin wouldn't just be a secondary force. It would be the mechanism that renders reality, stitching together pixels of spacetime to create the illusion of continuity. It's like discovering that the movie you've been watching isn't just images on a screen, but the result of countless microscopic mirrors flickering in perfect, hidden sync. What makes this phenomenon so electrifying isn't just the noise itself. It's the possibility that we're brushing against the limits of reality's resolution. Every anomalous blip in the data, every unexplained tremor in the detectors, could be a clue that gravity isn't the only architect of spacetime. There might be a collaborator, a shadow twin working behind the scenes, quietly shaping the universe's code. And if we're right, the next generation of experiments more sensitive, more precise won't just detect this noise, they'll decode it, revealing the hidden language of the cosmos. Gravity has always been treated as a fundamental force, one of the universe's bedrock rules, as basic as space and time themselves. But what if we've had it backward? What if gravity isn't a primary force at all, but something that emerges from deeper, more chaotic processes, like waves rising from the ocean's churn? This is the bold claim of emergent gravity theory, a revolutionary idea that flips our understanding on its head. And if it's correct, gravity's shadow twin might be the missing piece that makes it all click. Picture a crowded stadium doing the wave. No single person is the wave. It's a collective behavior emerging from countless individual actions. Similarly, emergent gravity suggests that what we perceive as gravity might be a side effect of microscopic interactions we can't yet see, a statistical outcome of entropy, quantum entanglement, or even information processing at the universe's smallest scales. Dutch physicist Erik Verland pioneered this idea, arguing that gravity doesn't exist as a standalone force but arises from the way matter organizes itself, like heat emerging from the motion of molecules. It's a cosmic sleight of hand where the universe's underlying complexity creates the illusion of a force we've taken for granted. Here's where things get even wilder. If gravity is emergent, its shadow twin could represent a secondary layer of this emergence, a hidden structure beneath the surface, tweaking gravity's behavior in ways we're only beginning to detect. Imagine two projectors casting overlapping images. The first creates the gravity we know, while the second, fainter one subtly distorts it, explaining anomalies like galaxy rotation curves or the universe's accelerated expansion. Modified versions of emergent gravity propose that this shadow layer might activate under extreme conditions near black holes, in the early universe, or at the edges of cosmic voids, where the usual rules seem to break down. It's like discovering that the ocean's waves aren't just driven by wind but by hidden currents beneath, reshaping the surface in ways we never expected. The implications ripple across physics. Emergent gravity could dissolve the need for dark matter, reinterpreting its effects as artifacts of this deeper, information-driven process. Galaxy clusters wouldn't require invisible halos to explain their motion. Their gravity would naturally strengthen in ways that mimic dark matter's pull, all thanks to the emergent interplay of spacetime's hidden architecture. Even dark energy might find an explanation not as a mysterious repulsive force, but as a thermodynamic gradient, the universe's way of balancing its books as it expands. Yet the most tantalizing clue lies in black holes. These cosmic paradoxes where gravity and quantum mechanics collide might be the proving ground for emergent gravity's shadow twin. If gravity emerges from quantum entanglement, an idea gaining traction in theories like the AD-S/CFT correspondence, then black holes could be holographic projectors, encoding information on their surfaces that manifests as gravity in our 3D world. The shadow twin, that might be the other half of the entanglement, a hidden partner ensuring the information isn't lost but translated, like a cosmic interpreter whispering between dimensions. Critics argue that emergent gravity struggles to match the precision of general relativity in all scenarios, but its proponents see these gaps as opportunities. If gravity's shadow twin patches the holes adjusting the emergent math where it falls short, it could unite quantum mechanics and relativity in a way no other theory has. The universe, after all, loves layers. From fractals to galaxies, complexity often arises from simple rules repeating at different scales. Why shouldn't gravity be the same? Whether it's a cosmic illusion or a deeper truth waiting to be decoded, emergent gravity forces us to confront a humbling possibility. The force that shapes galaxies, bends light, and pins us to the Earth might not be fundamental at all. It could be a mirage, a shimmering reflection of something far stranger, lurking just beneath the surface of reality. And if that's the case, the universe's greatest mysteries might not be hidden in the darkness. They might be hiding in plain sight. From the way galaxies spin too fast at their edges to the eerie voids where matter refuses to gather, the cosmos is filled with whispers of something unseen, a force working alongside gravity, bending the rules in ways we can't yet fully explain. These 40 anomalies aren't just scattered curiosities, they're pieces of a puzzle, each one hinting that our understanding of gravity might be incomplete. Think of it like watching a play where the actors move flawlessly, yet the stage itself seems to shift underfoot. There's a stagey hand we haven't met, quietly adjusting the set behind the scenes. What makes this idea so thrilling isn't just the mystery, it's the sheer scale of what's at stake. If gravity has a shadow twin, it wouldn't just tweak a few equations, it could rewrite the story of the universe. Imagine discovering that the force holding your feet to the ground, the same force guiding planets and shaping galaxies, is actually a partnership, a cosmic collaboration we've been unaware of until now. The implications ripple across everything from black holes to the Big Bang, offering fresh answers to questions that have puzzled scientists for decades. But here's the real magic. We're living in the era where this mystery could unravel. Telescopes like the James Webb Space Telescope peer deeper into space and further back in time than ever before. Particle colliders probe the fabric of reality at energies that might reveal hidden forces. Even gravitational wave detectors, those exquisitely sensitive ears listening to the vibrations of spacetime, could catch the faint echo of gravity's unseen companion. Every anomaly we uncover, every deviation from the expected, is a clue waiting to be decoded. This isn't just about filling gaps in textbooks. It's about the joy of discovery, the thrill of realizing the universe still has secrets to share. Whether you're a casual stargazer or a devoted physics enthusiast, you're part of this moment. The next breakthrough could come from a lab, a telescope, or even a curious mind connecting dots no one else has seen. So keep looking up, keep asking questions, and stay open to the wonder of the unknown. After all, the greatest discoveries often start with a simple thought. What if we're missing something? If this journey through cosmic mysteries has sparked your curiosity, don't let it end here. Hit like, subscribe, and join the conversation below. What's the most baffling gravitational anomaly you've encountered? The universe is vast, strange, and far from finished surprising us. Together, let's keep exploring the edges of what we know, because the next chapter in this story might be written soon.